Alrighty, howdy folks. In all my classes, that's how I start. I say howdy folks. I like it that way. And some students said, "Man, I miss your howdy," and so please forgive me if that annoys you. I hope it doesn't. Anyway, let's get to section 7.2 trigonometric integrals. First, let's deal with all the stuff that we know, all the trigonometric functions whose integrals we already know, which come from the derivatives that we know of those trig functions. For example, ddx of sine x is cosine x, right? The derivative of sine x is cosine x. Immediately from that you can say, aha, that must mean integral of cosine x is sine x plus c, right? Cool. So we know integral of cosine x now. Similarly, the derivative of cosine x is negative sine x. So the integral of negative sine x is cosine x. But then you multiply both sides by negative. You just get integral of sine x to be negative cosine x. And we add a c. Somebody might be feeling, hey, wait a minute, man. Like if you aren't you supposed to get negative cosine x minus c? How come you got a plus c? Well, c is just an arbitrary constant, right? So whether you subtract the arbitrary constant or add the arbitrary constant, it doesn't make a difference. In the sense, let's say you work a problem out and you used plus c, case 1, and you get c equals positive 2, right? Let me repeat that. If you said plus c and somehow you are able to evaluate c, it turns out to be positive 2. Then if you had used negative c instead, the same thing would have ended up being with c equals negative 2. So negative of negative 2 is positive 2. So eventually the constant would have been the same. Okay, so it doesn't matter whether we say minus c or plus c. I was going to tell a real life joke. Okay, maybe I'll go ahead and tell you that. In fact, when it comes to this constant, you don't have to just say plus c. You could say plus natural log of c if you wanted to. And in fact, when you get to differential equations, there is a place where you are better off actually saying natural log of c is the constant, right? Or if the only problem with some of those things is, do you cover the entire range? Let's say c could take on any real number value. Does a natural log of c cover any real number value? Yeah, that does. But could you say the constant is sine c? Yeah, technically there's nothing wrong. But then what if the actual value of the constant ended up being, say, 10? Then you will never find a c such that sine c is equal to 10, right? So theoretically you can use natural log of c, e to the c, sine c, all of these things. But as long as you're conscious of that little problem, it's okay. And I told you I'll tell you a joke. I had a student a long time back, and in their class I said the same thing. Hey, you can use anything for a constant. And then I gave a test, and one of the students, as I was grading, I looked at it. Everything was fine. And the guy said plus instead of a c. I noticed that he had something like e to the sine of secant square natural log of 2c minus 3. And I looked at it and I went, what? Where did he get this from? And oh, okay. He didn't want to say simply C. He wanted to say this complicated thing because I said you can pretty much say anything as a constant, right? And then I looked up who the guy is and I saw the name. Ah, that guy, yeah. Okay. And so when I handed the test back, uh, after everybody left the class, I stopped him and I said, "Hey, why do you do that, man?" And he gave a very profound answer. He just shrugged his shoulders and went, eh, that's it. All right. Okay, let's move on. So derivative of same thing, derivative of tangent x is secant square x, so integral of secant square x is tangent x plus c, cotangent secant, right? All of these things you know. I'm not gonna go through patiently. You can see. But then when we got to tangent x, that was not so straightforward, right? There was no the derivative of something was equal to tangent x. We never had anything like that. So when it came to tangent x, the integral of it, we had to resort to the u substitution method. We had to say, aha, first let's write tangent x as sine x over cosine x, and then plug in u equals cosine x, then du is negative sine x dx, and so that becomes negative 1 over negative integral 1 over u du, and which is negative natural log of absolute value of u plus c, and then right? We did all of this. But it's a good idea to go ahead and memorize this. Integral of tangent x dx is negative natural log of absolute value of cosine x plus c. Cool? And let me ask you, would it be okay for me to write this negative natural log of absolute value of cosine x as natural log of positive natural log of secant x? If I said that, would that freak you out, or would you go, oh, I see, I know what you did, man? Can you? Cool. Here is the idea, right? This, when we have a times natural log of b, would you agree that is nothing but natural log of b to the a? So can we write this negative natural log of, I'll drop the the absolute value, negative natural log of cosine x. Can I write this as natural log of cosine x, the quantity raised to negative 1? Cosine x raised to negative 1, ain't that equal to 1 over cosine x? Now, ain't 1 over cosine x just secant x? That's what I'm talking about, right? So this is natural log of secant x plus c. Okay, so sometimes you may want to write the integral of tangent x as natural log of positive secant x, positive natural log of absolute value of secant x too. Okie doke. Similarly, proceeding, we get integral of cotangent x is equal to natural log of absolute value of sine x plus c. Cool. Next. Ooh, 3-star problem. Integral of secant x. We have so far integral of sine, cosine, tangent, cotangent, but what we do not have is integral of secant x, and let's try to figure out what that is. Any idea how you would proceed? Hey, I'll write the secant x as 1 over cosine x, man. Great idea. Now then what do? Try some other method. If you can, then I'm sure you can publish a paper on it, right? But check this out. What? Yeah. Multiply both the top and the bottom by secant x plus tangent x. That's the trick, right? And the next part of the trick is set u equal to secant x plus tangent x, the denominator. What happens if you do? You get du equals secant x tangent x plus secant square x, the quantity times dx. And we can factor out a secant x. And we end up with this. Lo and behold, the numerator is exactly what we have here. So, lo and behold, the whole integral reduces to 1 over u du, which means that's equal to natural log of absolute value of u plus c, and replace the u with the secant x tangent plus tangent x, and you're done. Isn't that neat? Now, you might ask, hey, how did you know to multiply and divide by secant x plus tangent x and then plug in u equals secant x plus tangent x? Right? How did you know that? I mean, where did you come up with that idea? I shamelessly copied that idea. Yep. In this case, I don't mind admitting that it's just a shameless copying. Because some genius long time back somehow sat down and needed the integral of secant x, and he's like, dang, how do you figure this out? And must have tried all kinds of things and finally happened upon this, because that person is a genius. When I say guy, it could be a girl too. I don't know who actually came up with this, and probably published a paper. And from then on, all textbooks started publishing this, and then on, all teachers like me just said, okay, let's not reinvent the wheel, let's use what somebody else already figured out, and we are shamelessly using it. As simple as that. And guess what? From now on, you will also shamelessly copy this idea. As simple as that. Cool? Alright, the most important thing is integral of secant x dx, folks, is natural log of absolute value of secant x plus tangent x plus c. Now, for homework, I think it's a good idea for you to show that integral of cosecant x dx is natural log of absolute value of cosecant x minus cotangent x plus c. How would you proceed? Multiply and divide by cosecant x minus cotangent x, and set u equal cosecant x minus cotangent x, and do that stuff, and you'll be able to show that in fact that's what this ends up being. Cool? Yeah, that's okay. I was going to say something else. Okay, let me not tease you. For the nerds in the class, can you show that this is in fact equal to negative natural log of absolute value of cosecant x plus cotangent x plus c? What? Negative natural log of absolute value of cosecant x plus cotangent x. That's also an equally valid answer. Can you show that? Okay, just for the interested people. Cool. Let's move on. When evaluating integral sine to the mx cosine to the nx dx, strategy depends on the values of m and n. Let's see. Integral sine to the 6x cosine cube x. Does that look like integral sine to the mx cosine to the nx dx? It does. Cool. So what should we do? Well, is the power of cosine odd? Yep, the power of cosine is odd. In that case, you save a factor of cosine. Save a factor of cosine? All that means is cosine cube x, write that as pull a cosine x out of it, making it cosine square x times cosine x. That's what saving a power of cosine means. And write like this. Cool. With what idea? With the idea that you're going to substitute u equals something so that du becomes cosine x dx. Did you follow that? In the next step, we are going to plug in u equals something so that du becomes what you saved, cosine x. You saved a cosine x factor, right? Du becomes cosine x dx. Tell me, what substitution should we make for u so that you get du to be cosine x dx? Yep, you're right. Sine x. So we'll make u equals sine x so that du becomes cosine x dx. Now, would that work? What happens to sine to the 6x? Oh, that just becomes u to the 6. What happens to cosine x dx? Becomes du. But uh-oh, we got this cosine square x. What are we going to do about that? Aha. Could we not write cosine square x as 1 minus sine square x? That's the idea. So you replace the cosine square x with a 1 minus sine square x, and now you're ready to make all the substitutions. And simply becomes u to the 6 times 1 minus u squared du. Distribute that and integrate it, and you're done. Piece of cake. Right? The whole thing is simple only when you recognize this particular method. This is the strategy that you need to adopt anytime you see something of this kind. Okay? So we looked at cosine being an odd power. Let's look at some other cases. Is the power of cosine odd? Nope, it's even. Oh, wait, power of sine is odd. Well, there is a strategy when the power of sine is odd, which is not too different from this when cosine power is odd, which is you save a factor of sine. Now, any ideas what to plug in for u? You plug in for u in such a way that du becomes sine x dx. And negative sine x, if you end up, that's okay. That the idea is you plug in u equals cosine x and du is negative sine x dx. So that means we are clear about cosine to the 8x becoming u to the 8 and sine x dx becoming negative du. What about sine to the 4x? We need to write that in terms of cosine. So would this work? Isn't sine to the 4x the same as sine square x, the quantity square? Now, couldn't we write sine square x as 1 minus cosine square x? So that sine to the 4x becomes 1 minus cosine square x, the quantity square. That's the idea. Cool. Now we are ready to make all our substitutions and just patiently distribute, multiply, and integrate. I'm sure this is not difficult for you at all. Cool. So, what two cases did we consider? Power of cosine is odd, power of sine is odd, right? Logically, what's the next thing? Both sine and cosine have even powers. That's what we need to do. But before we get to that special case, I have to ask you to recall some important identities, trig identities. Did you know this one? Did you remember this? Cosine 2x is cosine square x minus sine square x. Hey, but that's equal to 1, man. No. Cosine square x plus sine square x is 1, but cosine square x minus sine square x is not equal to 1. Not as an identity. So cosine 2x is equal to cosine square x minus sine square x. Well, that's one version of cosine 2x. Are there other versions of it? Yeah, there are two more versions. What are they? Well, we can replace sine square x with a 1 minus cosine square x. Right? We can replace sine square x with a 1 minus cosine square x. Or we could replace cosine square x with a 1 minus sine square x. When we do that, first I have replaced cosine square x with a 1 minus sine square x, giving us 1 minus 2 sine square x. That's the second version of cosine 2x. A third version, like I promised, we will replace sine square x with a 1 minus cosine square x, and that gives us 2 cosine square x minus 1. Now you might be wondering, why man, why are you doing all of this? That's because we can now take that version cosine 2x is 1 minus 2 sine square x and solve for sine square x. Well, all this nonsense about subtract a cosine 2x from both sides, add 2 sine square x to both sides, blah blah blah. So you get this and figure and divide both sides by 2, and you end up getting sine square x is 1/2 1 minus cosine 2x. And that is a very important thing that you need to memorize. If you cannot memorize it, at least be able to derive it quickly, like how I have shown there, right? Similarly, if we use the other version of cosine 2x, we end up with 2 cosine square x minus 1 and solve for 2 cosine square x and then divide both sides by 2, and you get cosine square x is 1/2 times 1 plus cosine 2x. Very important results. Why did we need this? Why did we digress and talk about this? I told you that the only remaining case for us is for the integral of sine to the mx cosine to the nx dx. We looked at cosine being odd power, then sine being odd power, but what if neither is odd? That is, both cosine and sine are even powers. Here is the idea. For all the even powers, we replace sine square x. If we see a sine square x, we'll replace with 1/2 1 minus cosine 2x. If we see cosine square x, we replace 1/2 1 plus cosine 2x. That's the idea. That's why we needed to digress and talk about this. So, what's a simple problem? What's integral sine square x dx? Please do not say cosine square x. I beg of you, do not say that, because that's not at all true. The integral of sine square x is not equal to cosine square x, or oh no man, negative cosine square x. No, not even that. So how do you do this? Well, just like I said, we need to use the power of sine is even. We substitute sine square x is equal to 1/2 1 minus cosine 2x. And when we do, it just simply becomes, we can yank the 1/2 out, and integral of 1 is x, and integral of cosine 2x is 1/2 sine 2x. And so there's already a 1/2 on the outside, so 1/2 times 1/2 is 1/4 sine 2x. Right? So this is how you solve integral sine square x. Cool? Obviously, if I were you, I would immediately figure out what is integral of cosine square x. Right? That's a curious thing to do. All right. What about sine to the 4x? I love this problem. Integral sine to the 4x. Well, isn't sine to the 4x the same as sine square x, the quantity square? And so for sine square x, we'll plug in this guy, 1/2 1 minus cosine 2x, and we'll square the whole thing. And now we'll distribute or FOIL this whole thing out, and we end up with this. Can we integrate 1? Yep. Can we integrate 2 cosine 2x? Yep. Can we integrate oh no. What? Cosine square 2x. How do we integrate that? But notice, that's an even power of cosine. So that means we will resort to the same technique. we know that cosine square x is 1/2 1 plus cosine 2x. What? We know cosine square x is 1/2 times 1 plus cosine 2x. So, any idea what cosine square 2x would be? That's the key. That just becomes 1/2 1 plus cosine 4x. Can you see that? If you had cosine square x, we would have 1/2 1 plus cosine 2x. But instead of a x, we have a 2x, so we should have a 2 times 2x, which is 4x. That's what's happening here. Cool? All right. So if you understand that part, then the rest is all straightforward. 1 plus 1/2 is 3/2. There's a 1 here and there's a 1/2 here, plus 1/2 times 1. So that adds up to 3/2. And so this whole thing becomes this. And each term is easy to integrate. And the final answer ends up being this. I like this problem a lot. I would suggest that you should figure out integral of cosine to the 4x immediately on your own. Process would be very similar. Cool. How about this? Well, sine square x can be written as 1/2 1 minus times 1 minus cosine 2x, and cosine square x as 1/2 1 plus 2x. Go ahead and make those substitutions, and what happens? 1/2 times 1/2 is 1/4. 1 minus cosine 2x times 1 plus cosine 2x. That's what we would be left with inside the integral. Would you agree? 1/4 comes out. But then isn't that in the form of a minus b times a plus b? Which is a square minus b square, 1 minus cosine square 2x. Right? Does this guy look like a minus b times a plus b, which is a square minus b square? So this is 1 minus cosine square 2x. But 1 minus cosine square theta, isn't that equal to sine square theta? So shouldn't this be simply sine square 2x? Right? 1/4 times integral of sine square 2x. Okay, how do you evaluate sine square 2x? Oh, even power of sine. Again, use 1/2 1 minus cosine 4x. Right? And the rest is straightforward. That's the idea. Very nice problem. Next, when evaluating tangent to the mx, secant to the nx dx, strategy depends on the values of m and n. Okay, if the power of secant is even, we save a factor of secant squared. So that means we'll write like this. We saved a secant square x. You remember this strategy? Why do you save a secant square? Why do you save a cosine like that? So that you are going to do a u substitution where du turns out to be whatever you saved times dx. So we saved secant square x dx, secant square x. So secant square x dx should be your du. So u should be tangent x. That's the idea. So we're going to plug in u equals tangent x, du equals secant square x. But then what do we do about this secant square x? Write that as 1 plus tangent square x. And then make the substitutions. That's it. And the whole thing becomes straightforward. Cool? Next, tangent cube x secant to the 5x. If the power of a tangent is odd, then save a secant x tangent x. Okay, so That means we will rewrite this as tangent square x secant to the 4x secant x tangent x dx. U equals something such that du is secant x tangent x dx. So the answer is u is secant x. And so we know the secant to the 4x becomes u to the 4, but tangent square x, we will write that as secant square x minus 1. And then we make our substitutions. And so it becomes this, multiply, and integrate, plug back, and you are in business. Cool? Right. Integral tangent square x. Piece of cake. Did you get it? I told ya. Right? Simple problem. Tangent to the 4x. That's a good one. Oh, is that what I did? Yeah, that's a pathetic idea. That's a pathetic idea. Scratch this guy. Instead, I think a simpler idea would be integral tangent square x times secant square x minus 1. Cool? What? Yeah, man. Tangent to the 4x is tangent square x times tangent square x. And the second tangent square x, I'm writing as secant square x minus 1. So this becomes integral tangent square x secant square x minus integral, I'll go ahead and say dx, minus integral tangent square x. Tangent square x is secant square x minus 1. I'll write like that. And now if we plug in u equals tangent x, then du is secant square x dx. And so this becomes tangent cube x over 3 minus integral of secant square x is tangent x plus 1 dx is plus x plus c. That's it. Right? Tangent cube x. Man, look at the penmanship. I'm not able to, I got this screen not folded, and so please bear with me on that one. I apologize. But this is a much simpler method than what I did there. Oh yeah. What did I do? Nonsense. Not a good idea. You end up getting the same answer though. No, check this out. I forgot to delete that slide. I did do... Oh, I'm an idiot. Yep, this is a much better way. Cool? Alright, next. 3-star problem, integral secant cube x dx. Yeah, I like this. Check this out. I equals. Why'd you say I, man? You remember why we had to say I in integration by parts? Same thing happens here. Who would have thunk? Did you know you have to use integration by parts to figure this integral? Yep. When I first saw it, I was like, no, you gotta be kidding me. Yeah, integral secant x times secant square x dx. u equals secant x, dv is secant square x dx, du is secant x tangent x dx, v is tangent x. Okay, that's what you do. And you come here and say this is uv minus integral v du, you get this. Okay, but how do you evaluate integral secant x tangent square x dx? Hey, wait a minute. Can we write this tangent square x as secant square x minus 1? Yeah, let's do that. So replace the tangent square x with a secant square x minus 1. And then we end up with this. We end up with, hey, we were trying to figure out integral secant cube x, and we ended up with a negative integral secant cube x dx. Not to panic, we'll replace this with an I. That's why I used I. Do we know integral secant x dx? Yep, that's a natural log of absolute value of secant x plus tangent x. So I replaced integral secant cube x dx with I and add I to both sides, divide both sides by 2 in the next step, and we're done. Cool. This is a very nice problem. So it's not at all intuitively obvious that we need to use integration by parts for this. That's why it's a 3-star problem. Okay, and the next one is integral of cosecant cube x. Could you please do that yourself? You proceed in a similar way. You say cosecant cube x is equal to cosecant x times cosecant square x dx, and plug in u equals cosecant x and dv equals cosecant square x dx and blah blah. Cool. That's a good idea. Next, oh yeah, do not say sine of a plus b is sine a plus sine b. Okay, sine of a plus b is sine a cosine b plus cosine a sine b. Similarly, sine of a minus b is sine a cosine b minus cosine a sine b. And what's up with cosine of a plus? Oh, what happens if you add these two things? The cosine a sine b's will add up to 0. The positive and negative will add up to 0. And we end up with sine of a plus b plus sine of a minus b on the left hand side, and on the right hand side 2 sine a cosine b. And so sine a cosine b is 1/2 of sine of a plus b plus sine of a minus b. And that's a very important result. Cosine of a minus b is cosine a cosine b plus sine a sine b. Cosine of a plus b is cosine a cosine b minus sine a sine b. If you add, you get 2 cosine a cosine b, from which you can figure out cosine a cosine b to be this. However, if you were to subtract the bottom from the top one, then you end up getting 2 sine a sine b. And you can solve that for sine a sine b, and you get this. Please take a good look at these 3 results. You have to know these results, because when it comes to solving certain integrals, this is just about the only way. If you knew these identities, you're done. If you don't, you are in trouble. Okay. Speaking of which, here comes trouble. Integral sine 8x cosine 3x. Does that look like integral sine a cosine b? That sine a, yeah, sine a cosine b. Isn't that sine of a plus b plus sine of a minus b? That's exactly what I did. I said that's equal to 1/2 sine of a plus b plus sine of a minus b. Right? And so that is 1/2 sine of 11x plus sine of 5x. And sine 11x is easy to integrate, negative 1/11 cosine of 11x. And sine of 5x, the integral is negative 1/5 cosine 5x. We're done. So integrating that hinges entirely on us knowing the identities. I apologize if I'm insulting your intelligence picking up a problem like this. Cosine a cosine b. 1/2 cosine of a minus b plus cosine of a plus b. So applied that, and you integrate, you're done. Cool. One last, I think this is the last problem. Let's see. 1 over cosine x minus 1. This is a simple, surefire way of giving me a heart attack. Which is, you say, aha, that's piece of cake, man. I'm going to write that as 1 over cosine x minus 1 over 1 dx. Straight cardiac arrest for me if I see that. No, big time, no, right? You cannot, what's the basic principle there? A over B plus C is big time not equal to A over B plus A over C. You shouldn't read that. So when I look at the size of this thing, when it's big like that, you should not read that as not equal to. You got to read it as big time not equal to, and you have to say it in a southern accent. Same thing is square root of a square plus b square. Is that equal to a plus b? Nope. Square root of a square plus b square is big time not equal to a plus b. Right? Don't ever make mistakes of this kind. Okie doke. So how do you do this? Check this out. Sometimes you need to be very clever about integrals. What if we multiply both the top and the bottom by a cosine x plus 1? Right? And when we do that, the bottom becomes a minus b times a plus b is cosine a square minus b square, so cosine square x minus 1. Cosine square x minus 1? That's okay. We know 1 minus cosine square x is sine square x, so cosine square x minus 1 would be negative sine square x. So we'll replace that with denominator with a negative sine square x, and then, okay, what do we do now? I'll split it into two fractions. What did I say? Split it into two fractions? Is that okay? Can I say this is cosine x over negative sine square x plus 1 over negative sine square x? Can I split like that? Yeah, you can. But you just said you cannot. No, that's not what I said. But I swear, Dr. Sam, you just said you cannot do that. No. Here is what I said you can't do. I said a over b plus c is big time not equal to a over b plus a over c. Right? But did I tell you that you can't say this? A plus b over c is a over c plus b over c. Is that okay? Perfectly okay. There's nothing wrong with saying a plus b, the quantity a plus b over c is equal to the quantity a over c plus the quantity b over c. That is perfectly fine. Cool? All right. So we end up with splitting that, and that ends up being, what did I do here? Let me erase all of this then. And that's equal to, what did I do? Well, I split the denominator. I split this into 1 over sine x times cosine x over sine x. And that is because I wanted to say this is cosecant x and that is cotangent x. And why did I do that in turn? That's because we know that integral of cosecant x cotangent x is equal to 1. What was I thinking, man? Integral of cosecant x cotangent x is negative cosecant x. I'm sorry. Lapse of concentration. Minus negative cosecant x becomes positive cosecant x. Integral of cosecant square x is negative cotangent x or minus negative cotangent x plus cotangent x plus c. Cool. You got to solve a lot of problems in this one to get a thorough grasp of stuff. Okay. All right.